Hello. This notebook goes all the way down to the lowest level of Keras and PyTorch APIs. We built custom layers from scratch, composed them into a custom model with residual connections, implemented as GD with Momentum as a custom optimizer, and finally write a complete training loop by hand, replacing model.fit entirely with our own gradient tape logic. Cell 1 and second consist of import and data. We import TensorFlow, Keras, PyTorch, and standard utilities, then load Fashion MNIST in two forms. In as 28 by 28 image tensors for the convolutional experiments, and as flattened 784 dimensional vectors for the MLP and residual regression experiments. Both forms will be used in different sections of the notebook. Moving ahead, we have custom layers. The theory cell explains the three methods you need to override when subclassing. Keras.layers.layer. The build method is when you create weight tensors with add weight. It is called exactly once on the first pass through the layer. When the input shape is known, the call method defines the forward pass logic. The getConfig method returns a dictionary so the layer can be saved and reloaded. We implemented 4 custom layers. Exponential layer is the simplest. It is it applies an element-wise exponential transformation with no learnable parameters, making it useful as a final layer for predicting strictly positive quantities like counts or rates. MyDense re-implements a standard fully connected layer from scratch, creating a kernel weight matrix and a bias vector inbuilt. Then computing the matrix multiplication and bias addition in call. We verify that if it produces exactly the same parameter count as the built-in Keras dense layer. Next, we add Gaussian noise. This adds random Gaussian noise drawn from a normal distribution with a standard deviation sigma during training, but passes the input through unchanged at inference time. This acts as a form of Tikhonov regularization that forces the network to learn smooth, noise-robust representations. Finally, my layer normalization computes the mean and variance across the feature dimension of each sample independently, then normalizes and rescales using learnable gamma and beta parameters. Next, we compute and compare no noise versus Gaussian noise versus layer norm. We then run an A/B comparison, training 4 small networks, one using MyDense, one add Gaussian noise, one adding my layer normalization, and one using all 3 custom layer together. The combination model achieves the best generalization, confirming that the custom layers are functioning correctly and contributing meaningfully. Next, we have a residual block and residual regressor. The theory cell explains the vanishing gradient problem that motivated residual connections in very deep network. Gradients shrink as they propagate backwards through many layers, eventually becoming too small to update the early layers meaningfully. Hielet solved this in 2015 with the insight that instead of learning a full transformation, each block only needs to learn the residual, the difference between its output and its desired output. The skip connection adds the input directly to the block's output, creating a highway for gradients to flow backward through the network without passing through any nonlinear layer. Residual block subclasses keras.layers.layer. Residual regressor subclasses keras.model and stacks multiple residual block instances into a full classification network. We then run a control A/B test, a plain deep network with the same number of parameters but without residual connections versus the residual regressor. The residual version converges faster and achieves higher validation accuracy. demonstrating exactly why skip connections became ubiquitous after the original RESTnet paper. The PyTorch equivalent residual block PT implements the same structure using nn.sequential with nn linear and nn batch normed. Moving ahead, we have this is all about the residual regression and plain deep network that we just discussed. Then we have custom optimizer. The theory cell shows the momentum update rule. Instead of stepping directly along the current gradient, momentum accumulates a velocity vector that is weighted average of all past gradient. This dampens oscillations in directions with high curvature, accelerates through flat regions, and helps the optimizer escape shallow local minima. My momentum optimizer in TensorFlow subclasses keras.optimizers.optimizer and overrides the apply gradients method. For each trainable variable, it maintains a corresponding velocity variable, updates the velocity using the momentum coefficient, and then updates the weight. Moving ahead, we can see the comparison here. Then comes the custom optimizer, my momentum optimizer PT. This subclasses optim.optimizer and stores the per parameter velocity tensors in the self.state dictionary, which is PyTorch's standard mechanism for stateful optimizer. Next, we have custom training loop. The theory cell makes the case for writing your own training loop. Model.fit is convenient but opaque. It hides everything that happens between one epoch and the next. A custom loop gives you complete control. You can modify gradient between the backward pass and the optimizer step. Implement curriculum learning by reordering samples based on difficulty. Build generative adversarial networks where two models must be updated in alteration and add any logging and debugging logic you need. Moving ahead, we have custom training loop PyTorch. The PyTorch custom loop follows the same structure but uses the PyTorch EDM. Optimizer zero grade and loss backward and then optimizer step. It also uses our custom my momentum optimizer PT and one cycle LR scheduler and logs the current learning rate alongside accuracy so you can see the schedulers ramp up and cosine cooldown reflected in the training dynamics. The final summary table print validation accuracy for every experiment. The residual model consistently outperforms the plain deep network. The custom momentum optimizer reaches accuracy comparable to Adam, and the custom training loop model stacking all the custom layers together achieves the best overall result, demonstrating that all four components of this notebook work together correctly as a complete hand-built training pipeline. This was all about this notebook. Thank you for listening to the video.